Okay, so let us start. Yes. Okay. So here today we will try to discuss about, as I told you, continuous systems, and we have kind of finished one-dimensional maps for our case. So let us see. So what are continuous systems first of all? So continuous systems. So continuous systems are dynamical systems where time proceeds smoothly. All right, where time proceeds smoothly. Where time proceeds smoothly. Okay. So how you can model continuous systems? How you can model continuous systems? You can turn off this one also. This. Good. Yes. Okay. Yes. So how you can model continuous dynamical systems? Okay. Yeah. Let's see how it looks easy. Okay. Let's model continuous dynamical systems. How you can model continuous dynamical system is via differential equations. So mostly our job here would not be to solve differential equations. Those who might get afraid, no need to be afraid in the sense that you don't need to solve differential equations. The aim of nonlinear dynamics theory is to not solve the things, instead visualize the thing and make a deduction based on that theory. Okay. So we will see differential equations, but mostly it will be a graphical approach. How slopes are changing, how points are moving, like that. Okay. In your space. Fine. So in discrete systems, suppose like we had this x point, and you had how like you had this point, then we had a rule which f is a nonlinear map, right? Then you applied this is known as the initial condition, that is x naught ic initial condition. You applied the map f, it went to some other point, and you again apply map f repetitively for lot of times, for maybe what do I mean by a lot? It means like 10,000 iterations. Okay, so 10,000 iterations suppose, then I am interested in where the final point will go, where it will be converging to. Okay, so I have not shown you this carefully, but you have known about this, is they can either converge to a periodic orbit, they can either converge to a simplest case, that is a stable fixed point. Okay, they can converge to a periodic orbit, they can converge to a chaotic attractor also. Those concepts we saw via the cobweb diagrams. Okay, fine. So but this is for the discrete case, this is for the discrete map case. What happens in continuous systems? So in continuous systems, you just have like you have still the initial condition. You have the initial condition you can start from. Okay, say x naught. Then since it's a differential equation, this is your continuous system is modeled by a differential equation. The solution, the trajectory will be a continuous one. Okay, so you can see how it flows. Okay, you can ask me why not it is just a linear line, because yes, I am assuming that it's a general nonlinear system. So one nice thing about this is, which I will tell you later, is can this happen? It starts from a particular point, it goes there. Can this happen? Here something new is happening. What is happening is here no intersections, no self intersections was there, but here you can see there is a self intersections. Now my question is, can it happen in this continuous system? What do you think? What do you think? You can so just use your basic thoughts. Go to very basics. Okay. So suppose you had, suppose it can intersect. Suppose this can intersect, the trajectories can intersect. Then at the point of intersections, at the point of intersection, you will have two directions to go, isn't it? And that violates your ODE property. That is the uniqueness. Okay, uniqueness, and there is a uniqueness theorem, isn't it, in your ODE? So for each point you have a particular direction, but this is showing that for each point you have two directions to go. So that can intentionally tell you that uniqueness property of this ODE is violated. We'll come across that, so no need to worry. But even it is not a function. So actually, this is not a function actually. So see, this what you are seeing right now, right? This trajectory. This is not a function. Don't think of it as a function. This you get. This you get. Like this you get after you repeatedly apply that function. So it is not a function. It is like repeated application of that function, non-linear function. Okay. So and this creates your trajectory like this after you solve this ODE for a long time step. Fine. So that's an idea. Okay. Fine. So so good examples for this are like pendulum example. Like in a pendulum, like you can have this. This is the pendulum, and you know, you give it a kick and it goes like this till here, and also comes back again and like this. Okay. So it has also this angular momentum and angular velocity concepts, which you might have learned in these words. Is not new to you. Okay. Yes. Angular velocity and omega, they are the quantities which vary continuously. Okay. So therefore, these are the variables if for your continuous case, continuous dynamical system. Moreover, in discrete map, we have written xn plus 1 is f of xn, right? Where f is your rule here, and you iteratively apply, and your long-term interest is to see how this point is moving in your phase space, isn't it? So here, in this case, in the continuous case, in the continuous dynamical system, in the continuous dynamical system, it will be like x dot equals to f of x. Okay. So what is x dot? X dot is just a representation for dx by dt. That is rate of change of x, dx by dt, equals to f of x. This is just a one-dimensional continuous system, but you can have, just like maps, you can have 2D also. So for 2D, you can have x equals to f of xy, and y dot is say g of xy. Okay. And this is a two-dimensional system. You can also have a three-dimensional system, z dot h x y z, and this is also z z. 3D system. So in this 3D systems only you can have chaos. That's one of the group assignment which I've given to you, like Chua circuit and Drosser attractors, all this. But the ecology group who will show us for Lotka Volterra, it's a two-dimensional system, hence it will not show any chaos. Okay. That's the idea. But you can see how strong are one-dimensional maps. Even in 1D, 1D map can show chaos. But 1D system, this guy cannot show chaos. You will see that why it cannot show chaos is very intuitive. Okay. It's very intuitive. Anyway, because it doesn't have more degree of freedom at all. In one dimension, it cannot self-intersect itself. In one dimension, it cannot self-intersect itself. So what it can do basically, it can stay at one point, okay, and it can just go at either direction, this direction or that direction. It cannot do anything more than that in one dimension. Okay. But in your one-dimensional maps, we were seeing how the points were flickering around here and there. But you can see the main difference between this 1D map and 1D continuous system. In 1D map, there is no he has more freedom, because this point after this it can go. It doesn't. It has to be connected by a line. Okay, but in your continuous system, you can see they are connected by these curves. So they have a constraint that if I followed this, I cannot come back to this same point again. Else I'll self-intersect and I'll violate the property. That's the idea. Okay. So And even, yeah, those are the ideas. Maybe I can show you one example, but I think that will come later. Remind me that in two-dimensional maps, I'll show you an animation of a pendulum moving around and how it creates a face portrait. Okay. What is a face portrait? So if X and Y here, X and Y are your variables. So you can, yes. So if X and Y are your variables, then you can draw this continuous dynamical system starting from any initial condition and see how it goes. Okay. See how it goes. So this is known as a face portrait. Face portrait involves the state variables. What are the state variables? These are the variables that is changing in your dynamical system. So here x dot is f of xy, y dot is g of xy. So this is a 2D dynamical system, 2D system. Okay, fine. So yeah, that's the idea. And moreover, like non-linearity is a necessary condition for your chaotic phenomena to occur. But of course, you will see that in even if this 1D system is non-linear, it will not show chaos because it doesn't have that much freedom to move around. Mainly due to the ODE, the curves. Okay. All right. So yes. Okay. So what it means? What it means? Suppose x dot equals to f of x. We are considering 1D continuous dynamical systems. 1D continuous dynamical systems. Okay. So therefore, since it's one dimension, it will have only one state variable. So now I will not call it x. I'll start calling it a state variable. Okay. It is a state variable. And it looks like this, of course, x dot equals to f of x. Now I'll ask you, what is here? Instead of fixed point, the terminology, we will change it to equilibrium point. For maps, we were calling the point x star equals to f of x star, which satisfies this, then x star is a fixed point. X star is a fixed point of the map. Okay. But if you see x dot equals to f of x, here, instead, we will say that same fixed point, like kind of thing concept is, we will call it as equilibrium point. Okay. So you can see why we are calling it as an equilibrium point. Equilibrium is showing that your process is continuous. Okay. And how we compute it? Just set x dot equal to 0. You can see how different the condition is from this. X dot equal to 0, what it means? It is intuitive. Actually, it is intuitive in your case that if x dot equals to 0 and you get at a special point, that is f of x star equals to 0. X dot equal to 0 means f of x star something is 0. Okay. Then here x star is known as the equilibrium point. So x star is known as the equilibrium point in this case. F of x star equals to 0 here. Can you intuitively think why it is known as an equilibrium point without just admiring the definition? So x dot equal to 0, what does it mean? The rate of change of x is 0. That means x is not changing. Okay, like x is changing, like x is a constant, it is not changing. So you can see that is like a same concept as fixed point. Okay, but since it's a continuous process, we call this as equilibrium. Okay. So in order to find uh, your equilibrium point of a 1D continuous system, you have to set x dot equal to 0 or f of x equal to 0. So that's intuitive for a fixed point. So fixed point, like equilibrium point, is again the simplest attractor possible. This is the simplest attractor. Okay. Attractor is, what is attractor? I have not covered in the class what is attractor. But what is an attractor is a very intuitive. If at some parameter values, as I told, if your system has a fixed point, stable fixed point, then your nearby trajectories will get attracted to that point. Okay. So therefore, that that is known as a stable fixed point or a fixed point attractor. Okay. Here similarly, if your x star is stable, we'll see what it means for being x star to be stable in this continuous system. But suppose x star is stable, then all nearby trajectories. Suppose x star is stable. Here is your x star. Then all of your here you started with all your nearby trajectories will approach this. Okay, all of your nearby trajectories will kind of approach this fixed point. So the equilibrium point. Sorry. So you can see this is a stable equilibrium point, isn't it? So and this is the simplest attractor possible. Why we are calling it as an attractor? Because nearby points, you can see the any point you take, nearby points, they are getting attracted to the fixed point here, to the equilibrium point here. Yes. So you might say, yes, there can be a case where they are repelling, where they're unstable. If it is unstable, as I told you before, if it is unstable and unstable in nonlinear dynamics, I follow two patterns. I write stable in blue and unstable in red. So unstable, suppose this fixed point is unstable. So what happens to this nearby trajectory? Suppose you start from here, it will run away from them. Okay. So this is like the stable one, this is unstable. So you can see why it is unstable. Nearby trajectories are moving out, but of course, if you start exactly at this point, then you will stay there. If you start exactly at that point, then your x dot equal to 0 is satisfied. So you have to stay there. But if you make a tiny perturbation, it will just move away. That's the idea. Okay. So yeah. So one good example I can give is like the psychology in this case. Okay. So the psychology is like you might be refraining yourself to eat a particular treat. Like suppose for my example, I refrain myself from eating a lot of chips. Okay. So what I do, like I have this chips packet with me here. Okay. So what happens is I eat the chips a lot. So I have to control myself. So how I control myself? I keep the chips in different room so that I can never see it. Okay. So, but if I make a tiny perturbation of just walking into that room, I'm in this room, but if 40, even 45, the chips packet is there, and unfortunately, I just went in 45. Then I just see, unbearably, I see the chips packet and I start eating. Okay. So that small perturbation can make divert from your commitment. Okay. So therefore, I'm telling you, when you are starting from here, of course you will stay there. But if you just make a perturbation, then it will move away. That's like unstable. Yeah. So therefore, it is important to know the perturbation scheme. Therefore, it is important to know how much perturbation can affect your system. Okay. So we'll see this. So therefore, this motivates us. This perturbation is more important, and it motivates us for something known as linearization. Okay. What happens nearby? So we are interested in examining the dynamics of the system nearby the equilibrium point. Okay. Yes, we are interested in examining the dynamics close to the equilibrium point. How we do it? So this is the philosophical way of saying, but how we can actually implement this in paper? Okay. How we can actually compute it? So for that, let x star be our equilibrium point. X star be our equilibrium point of the system x dot equals to f of x. Okay. Let x star be our equilibrium point of the system x dot equals to f of x. Okay. Then what happens? I'm taking a small perturbation around that around that equilibrium point. So how I can take the small perturbation? That small perturbation is x of t, and that is x star plus a small tiny disturbance. Okay. Here, something. You can take epsilon as well. So I have written in my notes eta, so I'm okay. You can take epsilon also. Following the tradition that epsilon is always small. Okay. So x star plus epsilon t, right? Then I ask you, since we are always interested in x dot, now we are more interested in taking the derivative on both sides. Okay. So what happens if you take derivative on both sides? D by dt of x of t. So what happens here on the right hand side? X star plus epsilon t, right? So d by dx dt of x of t is just x dot, nothing else. Yes. D by dt of x star. You know x star is a fixed point. For your particular system, it will just be a number. So therefore, derivative of a number is 0 because it is not changing itself. So therefore, this is 0 plus, plus yes. So plus what we should write? D by dt of epsilon t. This is equals to say epsilon dot t. All right. Fine with you? Fine with you, right? So we got that rate of change of x is the same as rate of change of the perturbation. Can you see from this equation? Rate of change of x, the state variable, is same as the rate of change of the perturbation epsilon. All right. So that's the idea here. But we can think of this from a different perspective. From a different perspective. Now I applied here. I'm applying derivative here. Now I will apply the function on both sides. Okay, I will apply the function on both sides. So you have x of t equals to x star plus epsilon t, isn't it? What I'm trying to answer here is take f on both sides, the rule which you are taking for this dynamical system. So f of xt equals to f of x star plus epsilon t. Okay, fine. I think it's fine. So it will soon go away. Okay. So why I'm doing this is trying to bring to your attention that how we can derive a stability condition. Okay. Of course, this derivation will not be important to biologist here or any other uh, course you have, but just to know that how we go through this phenomenon just by taking perturbations. Okay. Now, I think mostly DSCS people can help me in understanding this. Just by writing f of x star plus epsilon t, now your bells must be ringing in your mind, isn't it? Is the bells ringing? No, not ringing. Who? In which case bells are ringing? In on whose ears are ringing? Yes, this should remind you of Taylor series. F of x plus h. You have to evaluate a function variable not at x. You have the value of function at x, f of x. Now what you want to do? Evaluate the value of function at a small perturbation, that is x plus h, in terms of your known quantity, that is fx. So that's what the revolutionary work done by Taylor. Okay, what he did is, you can see h, you know. What do you know here? Fx value you know. H you know. How much perturbation? F of x plus h, do you know? No, you don't. So if you write f of x plus h in terms of the known quantities, without even solving that complicated function, you can solve the function for that value by doing the known quantities, by using the known quantities. So what is f of x plus h? It is f of x plus h times the derivative of f at x. Such kind of plan. Plus h times the derivative of f, yes, plus h square by 2 f prime of x, and so on. It's an infinite series, right? But you can appreciate this definition that just this is known to you. this is unknown to you. H is known to you. Now you can see f of x plus h, the unknown quantity, you are writing in terms of the known quantities. Okay, so that's how you actually use try to find the function value at a different point. Okay, at a nearby point. So same concept we will apply here. F of x star plus epsilon t. Same derivative, same technique. So can you tell me what's the case here? So f of xt equals to f of x star plus h. H is just like epsilon. So epsilon t, then f prime at x star, fine, plus epsilon t squared, f double prime of x star, and so on. Plus, yeah, it's not hot. It's higher order terms. Okay, higher order terms. Okay. So yes. So can we solve it more again? Can you help me in this? Okay. Now, can you tell me what is f of x star? What is f of x star? Huh? What? No, f of x star is x star in maps. F of x star is x star in maps. I told you here. F of x star is x star here. I told you for maps. For equilibrium point equation, you need x dot equal to 0. So in this case, I am asking you, x star is an equilibrium point. So what is f of x star? What is f of x star? Okay. Can you understand? Can you understand why f of x star is 0? X star is an equilibrium point and you have x dot equal to f of x. So f of x star is 0. Fine. Plus epsilon t times f prime of x star, right? Plus, yeah, the higher order terms, let it be. Can you help me in this now? Are you seeing something happening here? See, every step is coming with a interpretation. So I want you to make interpretation at every step. Yes, you have to tell me. I won't proceed. After this, what we want to do actually? So what you're expecting from this? Just think what we are doing here. We applied just a tiny perturbation, epsilon, and then we are analyzing the dynamics of this system. Okay. So how we did? We used the concept of Taylor series to approximate something unknown in terms of known quantities. There easily it got simplified. F of x star is 0. Higher order terms we are not interested in. That doesn't affect the dynamics much. Of course, we have to prove, but I'm skipping it. But I'm saying you, we reached here, but what are we getting it from here? Everything is there in the board. Everything is there. Okay, fine. F of xt, you got this quantity, fine. But what is f of xt? It is x dot. It is x dot. So what is x dot? X dot x is this x star plus epsilon t. Isn't it? Isn't I'll read it. Isn't this quantity known to you? Xt equal to x star plus epsilon t. So What is x dot? Take derivative on both sides. X dot is just d by dt again, right, of x. And what is x? D by dt of star plus epsilon t, right? What is this quantity d by dt of x star? 0. Plus, why one guy is disappearing? Epsilon dot t. So x dot equal to epsilon dot. Are you appreciating it? So when I write, let me write in red. Okay, when I write in red, x dot, what it is mean? X dot equals to epsilon dot t, that is f of xt, and f of xt equals to epsilon t times the derivative at x star. Now you can see, we reached to a very nice equation. What is that nice equation tells us about? Epsilon is your perturbation. And we are saying the rate of change of. Yes. Okay. X dot equals to f of x, isn't it? From this equation 2, what we got x dot? Epsilon dot. So just put it epsilon dot. On the right hand side, f of x, right? What you got f of x here? No, f of x is epsilon t f prime of x star. So that is like epsilon t f prime of x star plus higher order terms. So just yes, I should respect the higher order terms. Yes. So you can see now that we have an equation totally like on epsilon dot. This is what is this guy? This is rate of change of your perturbation. Epsilon dot is rate of change of perturbation, and that is equal to the perturbation into the derivative. Yes, you got it. So basically, you don't just worry about these equations. You should not worry about the equations. You just should take the juice out of these equations. What is the juice out of this equation? The juice out of this equation is if you have x dot equals to f of x is your 1D continuous dynamical system, and you have an equilibrium point x star where you have f of x star equal to 0. And what you do is you analyze the stability nearby that. So I do a perturbation, that is epsilon t. Okay. And then I am, and that is unknown to me. What is the dynamics of that perturbation? I use Taylor series in approximating an unknown quantity based on the known quantities. That's what this a bit of complicated equations look to you. But finally, what is that juice? That juice is this equation, epsilon dot equal to epsilon into f prime. Okay. That is saying how your perturbations are growing. How your perturbations are growing. This equation is actually the geometric interpretation of these graphical quantities in red. If your perturbation will just shoot out, then yes, this is the unstable case. If your perturbations is not growing, instead it is decreasing, then it is this case. So this is a very nice technique in understanding perturbations, wherever you want to know about perturbations. Okay. Welcome, wait. Anyway, so yeah. How you can solve this? How you can solve this? I will leave it out to you. I will leave it out to you that how you, perturbation. See, the perturbation, I can give you a very nice example. Okay. So you are there, right? You are there. So maybe let me take some other example. So like, yeah, suppose I am here. Okay, I am here. This is my stability point. Okay, this is my stability. Like I am always here. Okay. Okay. Let me give a very nice example. You have a pendulum. What you do? Take a cricket ball from Mr. Akrul Murli. Okay, take a cricket ball from Mr. Akrul Murli. Okay, and then you tie it with a thread and hang it on the wall. Okay, it always be right, isn't it? Always you see the pendulum lies here. Yes. What you do? Why is that? Okay, you should maintain the decorum of the classroom. You're going way outside of the classroom environment. Okay. Anyway, for Miss Halima, like you can see, the pendulum is here. Yes. So what you do is give a tiny perturbation. Okay. So you can you guys are making me laugh like anything. Okay. So you give a tiny perturbation to this. Okay. What will happen? It will just go on this side, right? Then do you think like it will stay there? Salima, do you think it will stay there? No. What it will do? Okay. Okay, it will swing. Fine. After that, so it will come back, right? So that's it. So this is the tiny perturbation you are giving. The kick is the tiny perturbation. Okay. So suppose like you are, I think like Halima and Anandik are there. So what Halima does is Anandik cracks a joke, and what Halima does is gives him a throw. Okay. Then Anandik gets shifted, right? So that's a perturbation. That's a perturbation. That's a good example of perturbation. Whether Anandik will return to its original position or will drift away from the original position on the like the body structure of Anandik. Okay. Yes, here frictions is there, so therefore always you will come back. But if you do this experiment in space, it will never come back. One of my personal interest is those who are, if you one of you guys go to space sometime later, okay, then take a double pendulum with you, okay, that's a chaotic pendulum, and run it and shoot me a video and send it to me. Okay, I want to see the double pendulum run ever again. I don't want that chaotic pendulum to stop. That's my interest. I have shown you the double pendulum, the chaotic double pendulum, isn't it? How chaotically it moves. But unfortunately, on Earth, it stops. I want to look at it going forever. Only can happen in space. Where? Where? No. That's why we fly in space. Yeah, if you go to moon, gravity is there. But if you are in the space, no. That's why if the spacecraft is going at a particular trajectory, it has to follow that particular trajectory. If if it just gets perturbed a bit, if someone sneezes, if you sneeze when you are outside of your space station, go. Always you float. That's what happened is also shown in movie. Gravity, yes. Very nice. I suggest you watch. Gravity of Float. Is it? That is too much detailed. I don't know. Maybe it can be there. You have to consider. If you say like that, then gravity of moon is also there. Yeah, we have to. I don't really know about much about that. You have to Google it. Okay. So let us return back from our ball example. Okay. So epsilon dot equals to epsilon t into f prime of x. Okay. So I'll convince you that epsilon t is equals to some epsilon naught, that is your perturbation at initial state, into e to the power, say, yeah, tell me what is the, yeah, tell what did I should write? Hmm? Perturbation spinning. Okay. Okay, make yourself aware that this is the case here. So since you can easily see this is the differential equation solution. That is that the perturbation grows according to this formula. Like epsilon naught, that is the starting perturbation, initial perturbation times exponential to the power of derivative of the function. Okay, fine with you. So you can see now if f prime at x star, what is happening? Is any issues? Is okay with you? So if f prime of x star, if f prime of x star is greater than 0, then this exponential will shoot up. This exponential quantity will shoot up, positive side, it will blow. So therefore you can see it will just like grow, like exponential growth is there. Exponential growth is there, and this is like unstable. Okay, this is like unstable. Can you make an understanding now? Here you can also use f prime of x for your stability. If f prime of x is greater than 0, it is unstable because it is exponentially blowing up. Okay. Now, if f prime of x star is less than 0, then you can see this f prime of x will decay. So this decays. Hence, this is stable. Now you can see how the condition got changed from your 1D map. In your one-dimensional map, you had the derivative of the function in the absolute value should be less than 1 if it is stable. Do you remember? Remember? Mod of f prime of x star evaluated at x star is less than 1 in your 1D map for it to be stable. And if it is greater than 1, it is unstable. But for your continuous map, so what we learned from here, from this derivation, is for a continuous map, for a continuous map, say x dot equals to f of x, and you have an equilibrium point x star. X star is an equilibrium point. That means f of x star, that is x dot, sorry, maybe that is, I'll remove that. Yes, that is 0. Yes, x star is an equilibrium point. That means f of x star is 0. Moreover, if you want to characterize point, if it is a stable equilibrium point, then f prime at x star should be less than 0. If it is an unstable equilibrium point, f prime of x star will be greater than 0. 0. That's what I'm telling you. That's what the difference is. Moreover, you are looking into the sign of f prime of x. It's not the modulus anymore. In your maps, in 1D, this is 1D ODE. In your 1D map, you had xn plus 1 is f of xn. Okay. And suppose x star is a fixed point. That means x star equals to f of x star. To categorize this stable or unstable, what you do? If it is a stable fixed point, if it is a stable fixed point, then the modulus of f prime of at x star should be less than 1. If it is unstable fixed point, the modulus of f prime at x star should be greater than 1. Can you understand this? So therefore, I told you in the beginning of the class, the conditions, the bifurcation patterns, everything will change depending on the type of dynamical system it is. And I told you there are two types of dynamical systems, maps and ODEs, flows, maps and flows. So for maps and flows, we have two different kind of conditions. I hope you can appreciate it. Okay. So I showed you intuitively why this is the case, why it is the derivative, why the derivative matters. So what we did in this example is we took a perturbation, okay, epsilon, and we saw how the perturbation is growing with respect to time. And we came across this differential equation. Everything boiled down to this differential equation here. So epsilon, which is the perturbation with time, is equal to the initial perturbation, that is epsilon naught, times the exponential power of the derivative at the fixed point. Okay. So now, if you want to say nearby the perturbation, if your f prime is greater than 0, the exponential is blooming up. So therefore, epsilon t grows. So therefore, you can see the trajectories are moving away, which I have shown here in this case. Okay, therefore it is unstable. Whereas if f prime of x star is f prime of x star is less than 0, then the exponential term is decaying. Yes. So what happens here? Then it is trying to converge to that equilibrium point, which is this case. So therefore it is stable. So you can both mathematically and geometrically think why f prime of x star greater than 0, the sign is giving you the nature of the equilibrium point, whether it is stable or unstable, whether the nearby trajectory will blow up or converge to it. Can you get it? Can you get the idea behind this? I hope you do. Okay. Now, as usual, you must ask, what happens? What happens if f prime at x star is 0? Okay. What happens if f prime of x star is 0? Then the concept we deduce fails. So this concept, what we have done here right now, maybe here, this concept like the small perturbation, okay, this is known as something known as linearization. Trying to see what happens nearby that fixed point is the concept of linearization. Okay, so therefore here, if f prime of x star is equal to 0, what fails? The linearization concept fails. Okay, because you cannot reduce. It will be just epsilon time equal to it. It will be just like a constant exponential factor, just like that. So you cannot reduce whether it is growing or shrinking, but it is always there. It is also not converging. So what it is doing? So you cannot reduce the dynamical behavior. So therefore linearization fails in this. So you have to do some more work in this. Okay, fine. Now let us take some examples. Okay. Right. So shall we have break or something? Okay, so let's have a break and after that we will start.